Okay, so what I want to talk about um, is so I was I was asked to talk more about like questions and what can how can machine learning help physics? That maybe I'm less qualified to talk about since I don't know too much about physics. And how can physics help machine learning? What I'll talk about that instead of I do want to talk about things a bit more concretely. So what I'll talk about is in the beginning I'll talk about my view about what is there to understand in deep learning. Why I mean what some the topic that right now I'm very interested in is understanding what's going on in deep learning. What are we actually doing there? In including some both concrete problems where I really think physicists can help me, and in fact, I've knocked on doors of physicists in University of Chicago, trying to like get them to help me understand things that they understand much better than me. And more generally, what type of why do I think that now is there's a lot of relevance for statistical physics in understanding deep learning? And hopefully towards the end I'll actually come around and try to talk a bit more generally about things. So we'll do it kind of reverse. We'll start with the specific and go to the general. So what I mean by understanding deep learning. So generally when I talk about understanding learning using any model class, there are three things you really want to understand. You want to understand, you know, we want to learn with the model class. This model class has to have small enough capacity so we can actually generalize. And we want to understand how well can we generalize when learning with this model class. Then we want to understand what can we actually capture with this model class. And also there's computational issues involved and we want to understand. So this is kind of the classic view of understanding learning with any model class. Um, and if I gave this talk, 5-ish or more years ago, then the picture I'd say is as follows. So the capacity of deep networks, or generalization ability of deep networks, is as you can think of it as how many samples do we need in order to generalize with the deep networks, we actually understand very well. And without getting too much in details, roughly this is captured by the number of parameters or the number of edges in a network. So if I have a network with some number of edges, then if I train the network using an amount of data which is scales with the number of edges, or strictly speaking, maybe number of edges times the depth, then I'll be able to generalize. And this is exactly the very, and we know also this is very tight characterizations of neural networks with a fixed size. And so this we actually understand fairly well. And then there's the question of the expressive power. So now we can understand, okay, we actually can, if we don't need that many samples in order to generalize a neural network, what can we actually represent with neural networks? So there's classic work about what we can represent with neural networks that says, well, we can represent anything with neural networks. And neural networks are dense in the space of all, depending on your metric, continuous, smooth, whatever functions. So we can approximate essentially any function with the neural networks, and these are great because we can represent anything. We can also represent like all functions over the hypercube with neural networks. The problem here is that in order to represent any functions, the number of units we need, the number of edges is huge, right? So for representing continuous function over RD, the number of units scales exponentially with the dimension. Or representing an arbitrary function over the binary hypercube, the number of units scales exponentially with the dimension. And so the number of edges will also scale exponentially with dimension. And that's not good for us because we said that for, is there actually a pointer I can use here? Does this work? No, okay. Physical pointer, even better. Okay, because we said that the number of samples we need scales with the number of parameters and number of edges, and so if in order to we can fit any function, but with a number of parameters that grows exponentially, so this is not good for us. Really, the question we should answer, the question we should ask is not what functions we can represent, what type of things we can present with a neural network, but what kind of thing we can represent with a small neural network, with a neural network which has a controlled number of edges, because that's when we can generalize. And there's lots of work and interesting things you can represent with small networks. Can represent all kinds of both specific things, like most importantly, like parities, which you cannot represent with linear predictors. You can talk about learning low-level features, mid-level features, high-level features, and represent all kinds of interesting things that way. And there's very convincing stories about that. But really, I would say that all these stories are not completely necessary, because I would say that in a much more because in some sense, not only can you represent any function with neural nets of a huge size, you can represent any function you care about using a very small neural net. And that's because if a function is computable in time t, you can represent it with a neural net with only roughly size roughly t. Okay, and since I would argue that you never want to learn something if the output of your learning is not something you can compute efficiently, then there's no point in learning it in the first place. So these are really all the functions you would care about, and indeed you can present any functions using a fairly small neural net. So this story so far is really compelling and says that neural nets are a great learning model. I mean, they're the universal learner. You can represent anything you'd ever want to learn using a small neural net, and you can actually fit it using a reasonable sample size which also only scales roughly linearly with the runtime of your output function, which is great. And then the only thing we don't understand is this computational issue, right? So if we actually had a method, and this is definitely true, if we had a method of taking data and finding fitting the parameters of a neural net in a way that minimizes the error in the data, then we'd have a universal learner. We could learn like anything we wanted. The only problem is we don't have such a method. So the problem of taking data and fitting a neural network with that data is hard. Okay? So it's NP hard, or hard in the worst case, already for like the smallest network that you can imagine. So a network with only a single hidden layer with 2 hidden units. Already there, the problem of even just deciding whether it's possible to fit the network exactly or not is NP hard. And you can have much stronger, so this is kind of a worst case hardness guarantee, but now you can say, well, what if I know my data actually is generated from a neural network, or maybe I even make some assumptions about the inputs being relatively, inputs being uniform, or what if, for example, you can say, well, yeah, but I can maybe use a much larger network and assume the data is generated by a much smaller network. And it turns out that all these things are kind of futile. So we have very, very, very strong results that tell us that even if you have data that's exactly generated by a very, very small network and then with a fairly benign input distribution also. So I think here I said this input, a single hidden layer with a number of hidden units is logarithmic in the input dimension. So a fairly moderate number of hidden units. And you have data that's exactly labeled by that. And even if you use a much larger network during training, or any model, or combination of networks, or whatever you know, whenever you want, there's no subject to appropriate complexity assumptions. There's no efficient algorithm that can actually always succeed in training. So what this tells us is that it's not, if you ask why do neural networks work, it's not, at least according to this classic understanding, it's not because you can really represent many things using a small network. Because we know that being able to represent something using a small network is not in any way an explanation for why we can actually learn it using a neural net. Because we know there are problems you can represent with a small network in which using no efficient algorithm, you would actually be able to learn using a small network. So rather what's going on here is that, a pessimist would say, and this is kind of what people I think said 10, 15 years ago, is let's just go home and use different methods because this is, these hardness results tell us that everything is lost and we can't do anything. But of course, what we see in practice is that for many interesting problems, we do succeed in actually learning them with neural nets. So what's obviously going on is that these problems have some kind of property, I'll refer to here as the magic property, that makes them learnable using a neural net. So in what I'd say, what I've said 5 years ago at least, is that they have some magic property that makes local search work. Okay? And what really the key to understanding neural networks is understanding what is this magic property and why is it that under this magic property I can actually train neural networks. So this is a bit similar to Lenka's third edge that she had in her triangle, the kind of assumption about the data. So what is this assumption about the data? And I would argue that we don't have the slightest idea what this magical property is. The only thing I can tell you is what this magic property isn't. This magic property is not being able to be representable by a small network. So if you go and ask, I don't want to pick on anybody specific, and also I'm actually not seeing somebody specific that I feel comfortable picking on. Ask a vision researcher, use your neural networks. Why are they good? And they say, well, neural networks are great for vision because they have the structure of low-level features and mid-level features. They really fit you can really capture the visual phenomena very well with the neural network. What they're explaining to you is this thing. but they don't. That thing doesn't need to be explained. We already know that you can capture basically much anything you want with a neural network. They're not providing that. That explanation provides zero evidence. Doesn't tell you anything about this magic property because again, we know that being able to be fit by a small neural network is not reason enough that you can actually train a neural network. Okay, so rather there's a different magic property, and again, I would claim we have no idea what this magic property is. Okay, so this is the talk from 5 years ago. And I think also for this, understanding this magic property, this is more similar, I think, to the type of things we saw in Lenka's talk, where we have this, subject to some property on the data. If we have enough data, then hopefully actually it becomes easy. And with this magic, we tweak this magic property. Maybe this property is not a binary property, but a kind of like a real valued property. And if we have enough of it, maybe it becomes easy. If we don't have enough, it becomes hard. And the problem is really just about the computational issue. So we understand the informational limit, we don't understand the computational limit. But actually, 5 years ago, we did an experiment that really, oh wow, I am, this slide talk, did this slide really take me? Time left, so I already spoke for over 10 minutes? My God, okay. This is really bad. Okay, so let's go time warp forward. Okay, so 10 years ago, we did an experiment that really changed my, at this rate, I'm going to speak for an hour and a half, that really changed my mind. And what we did here is we trained a bunch of neural networks of increasing size. And each one of these is separate. This is not time. This is just different size of networks. And what we see here is this is the training error. So the training error goes down as the size of the network increases. I mean, of course, because we can fit more things. The question is what happens to the test error. And the test error initially goes down. Interesting is what happens here when we're not fitting the data any better. What happens to the test error? So our standard view would tell us that at this point, the size of the network is larger, the capacity of the class is larger, the test error should go up. We should start overfitting. What we actually see is this, and you can see this consistently for almost all architectures in any data set, that the test error actually goes down. So we're actually fitting better and better and better. Now we're not fitting here because the approximation is better. I mean, this is already, we're approximating the training data perfectly, but rather the kind of the explanation for why we're getting better test error is probably because the capacity is going down, but the number of units is going up. Okay, so that suggests that the number of units is not actually the correct capacity control for what's going on. In particular, if we look at here, a network with 1,000 hidden units here already has many more parameters than training examples. So we should completely overfit the data. But we don't. We actually have pretty good test accuracy here. So there's actually two things here. One is, why is this going down? And the second, forget the fact that it's going down. Why is this even at only like something like 1 point something %? I mean, why isn't this like completely, just completely random, completely junk? Okay. So if we look at what's happening there, what we're finding is some global minima of the training objective. What we did here by training is we just minimized the training error. Okay, that's the only thing we did. So we find a global minima of the training error, and it actually has very small test error. Now, as I told you, there's many, many more parameters than training points, and so there are many global minimizers of the training objective. Okay? So let me plot a few more of these. Each one of these points is a global minimizer of the training objective. Any one of these would be a completely legitimate answer to the optimization problem of minimizing the training error. Okay? But many of them actually have very high test error, up to like junk random test error. Okay? So why is it, when we run our optimization algorithm, it's not actually though finding these ones. I actually had to work pretty hard in order to find these global minimizers. Okay? If you just run gradient, the way we train this is just run gradient descent, and what you get is to this one. Why is it that gradient descent actually finds something that generalizes well? Okay? And so what we suspect is going on here, and there's mounting evidence, is that what's going on here is that gradient descent biases us towards solutions that have small magnitude norm in some sense. And this norm or magnitude is really what's driving generalization. Okay? Now, the question is, what is this, when I say small magnitude or norm, the question is, which magnitude or norm? So what I plot actually here is some path norm that I'm not going to, it's some measure of the magnitude of the weights. Okay? But the questions we should ask ourselves now is, first of all, why, I plotted your path norm. I could have plotted a bunch of other things and also got a plot that looks kind of like this. What is the measure that we're actually it seems that this measure is crucial. It's not baked in explicitly into our learning rule. What is this measure that we're minimizing? And how is it that optimization algorithm actually biases us towards solution with this actually correct complexity measure? The real complexity measure is small. In particular, if I'm claiming that all this control, all the generalization coming from control some kind of magnitude, and that it comes just by the choice optimization algorithm, use gradient descent in particular, then if I change my optimization algorithm, I would expect to get different generalization properties. And we actually see this, okay? So, oops, actually, let's go here. So what we did here is we trained using two different optimization algorithms. Forget what they are. Let's call them the blue method and the blue method and the red method. And both of these methods succeed in finding a global optima. So all we're doing here is minimizing a training error. Both of these are perfectly fine optimization algorithms. Maybe one is a bit faster than the other. I don't care about that. This is the training objective, and both of them succeed in finding a global minima. But if I look at the generalization properties, and we see that the blue algorithm generalizes consistently better than the red algorithm. So in some sense, the blue algorithm is finding a better global minima. Now, better in what sense? It's not better in terms of the optimization problem. They're both global minima. It's better because it seems that whatever it is that it's minimizing is better for generalization. But I don't, it's not that I can tell you for neither the blue or the red one exactly what it is they're minimizing. Yes? But they're finding global minima. I know they're finding global minima because they're finding a zero-error solution, and the objective is not negative. So they're definitely finding global minima. So the issue here is not that they're getting stuck in some local minima. So they're just finding different global minima. Okay? Another example, SGD versus Adam, again, just think about it as the green algorithm, the blue algorithm versus the red algorithm. Both of them are going to converge eventually to the global minima here. The red algorithm is actually better in terms of optimization. It gets to the global minima faster. So if I put on my optimization hat, I should be happier with the red algorithm. If you look at generalization, though, the blue algorithm actually generalizes better. So it seems, again, to be biasing us to a better thing. And again, so the case I'm trying to make here is that when we look at we look at learning with deep networks, then what's going on is that our model, all our inductive bias, everything that tells us, what are this complexity measure we're actually minimizing, does not come from the model class, because the model class is usually that we're using uses huge networks with many more parameters than variables. They can essentially represent any function. Really, all the bias in terms of the kind of the model selection, biasing us towards which model we prefer, comes from the choice optimization algorithm. So really, the image you should have here is that we're optimizing. So I would argue that what we're doing is we're really optimizing. We said at the beginning that neural nets can actually capture any function. I think this is the real way to think about this, that we are really optimizing over the space of all functions. So when we're optimizing over the space of all functions, then, this is a meaningless optimization problem. Of course, I can fit the training data perfectly with some function, okay? The thing is that if I look at my landscape, then there are many global minima, okay? This is all the sort of zero-error solutions, the functions that perfectly fit the training data, okay? And I'm not really limiting my model class, okay? Because I'm using a network that's so big that it can completely fit the data in many ways. Essentially, I'm just optimizing over all functions. But what happens is I'm starting to optimize in some place, and I'm going to optimize using a specific method. So if you think of the global minima as the oceans, zero-error solution, ground level, you start optimizing on some hill, and you're going to get to a global minima. The question is which global minima you're going to get to. You're not going to get to the middle of the ocean. You're going to get to some beach. And which beach you're going to get to? You're going to get to a beach that's kind of close to where you started. But close in what sense? And this is where it depends on optimization algorithm. Different optimization algorithms are going to bias you towards different beaches that are close in different sense, and this is your real complexity measure. So let me give 2 or 3 examples to make this concrete, okay? The first example is it says here metrics reconstruction, but think of this as metrics completion, right? So you're solving a metrics completion problem. Here it says as metrics reconstruction of linear measurements. If your linear measurements are just indicators, it's just metrics completions. So you have a partially observed metrics, and I want to complete the unobserved entries. And the way I'm going to do it is by solve the optimization problem of searching over all matrices and minimizing the error on the observed entries. So this is a completely nonsensical optimization problem, okay? Because I'm not limiting my search in any way. It's all matrices, just as much as with searching over neural networks, I'm searching over all functions, okay? So this doesn't make any sense. Right? This optimization problem is way over-parameterized, just as like neural nets, and has many global minima, just like neural nets, okay? In fact, it's very easy to have a global minima here. Just fit the observed entries and put 0 everywhere else, or fit the observed entries and put 73 everywhere else, or put the Fibonacci sequence everywhere else, okay? So just minimizing the training error here doesn't actually get you anything, okay? Okay, but um, okay, so we're of course interested in okay, so this doesn't make any sense. Completely nonsensical optimization problem. And what we're going to do is just what we do in deep learning. We're going to make it even more nonsensical. Okay, so we're going to reparameterize w as u times v. Okay, and u times w is say n by n. U and v themselves, each one of them is n by n. So we didn't restrict your w at all. I mean, I can represent any w as u times v. In fact, in many ways. So instead of having n squared parameters and say 10n observations, 10 observations per row, I have 10n observations, and instead of n squared parameters, I have 2n squared parameters. Okay, this doesn't make any sense. All these same global minima still exist. Okay, so this optimization problem, as an optimization problem, is completely nonsensical, and just saying I found the global minima of that doesn't do me any good. Okay, but what we're going to do is we're going to optimize this with gradient descent over u and v, and ask what happens. Okay, so this is what happens. So what we're planning here, this is gradient descent on w. Okay, and if we do solve the optimization problem with gradient descent on w, and this is if I solve in gradient descent on u and v. So if both cases I get zero training error, I mean I fit the observed entries, big deal. It's very easy to fit observed entries. Okay, the question is what happens to my test error. Okay, and this is generated some simulated data when I actually generate some data which is approximately rank 2. Okay, but this doesn't help. The fact that the metric is approximately rank 2 doesn't help you at all. If you're doing gradient descent on W, you're just going to again fit the observed entries and not touch the other ones. So your test error is going to be pretty much random. Okay, but if you do gradient descent on U and V, then surprise, surprise, you actually generalize pretty well. And where is this generalization coming from? And again, it's not coming from the training objective. The training objective is nonsensical. Moreover, I'm going to change the optimization algorithm. So this is what happens if we do gradient descent with exact line search. I'm going to change it to a worse optimization algorithm, which is gradient descent with very small step sizes. So this is worse optimization algorithm. It will take me much longer to optimize. But then I actually, again, get zero training error eventually. But now I generalize even better. Okay, so what's going on here? Can we understand what's going on here? And the answer that, at least in this case, we can understand what's going on, more or less. So what seems to be happening here is that the solution we're finding here is the minimum nuclear norm solution. In this case, it will be exactly the minimum nuclear norm solution. So in particular, I would argue that if we do gradient descent with small enough step size, infinitesimally small step sizes, and start infinitesimally close to the origin, then not only are we going to converge to a zero error solution, that's not a big deal, I mean, that's easy, but we're going to converge to the minimum nuclear norm zero error solution. Okay? And now, note that this doesn't explain on its own, doesn't explain generalization. This statement is only a statement about optimization. Whatever you do, even if you initialize, some problems are not reconstructible. If the observations are completely random, you can't hope to reconstruct. You're still going to go to the minimum nuclear norm solution. But now there's a separate piece that we already know how finding a minimum nuclear norm solution is actually good for generalization. For example, we can actually, if the matrix is approximately low rank. Okay, so note that we separated it into two parts. One part is I told you what you're actually doing. It's not just that you're fitting your model, but you're fitting your model biasing towards the nuclear norm solution. And now you have a separate theory of why minimizing the nuclear norm is actually a good thing. Okay, now I should say that when I say that we understand what's going on, that's not actually completely true. And this is one place where I maybe would like some help from you guys. And you can look at this example of what happens later on. So again, our conjecture is that you always converge to the minimum nuclear norm solution. We can only prove this rigorously. This always happens if your observations commute, which is definitely, it is the case for symmetric reconstruction problems. It is not the case for matrix completion, for example. There's some follow-up work by Tengyu Ma and his students that proved that even if the matrices do not commute but obey some incoherence condition, then also you can prove you get reconstruction. And we argue that in general, for any observation matrices, you minimize the minimum nuclear norm. When they say we argue, I mean this is like argue by speaking very loudly and confidently, but without much basis behind it. I mean basically we have a bunch of empirical experiments and some hand-waving arguments that if things don't go crazy, then this is what happens. Really, what this boils down to is analyzing the limit of time-ordered exponential. This is an expression I learned from just a few years ago from when I again went and knocked on a door of quantum physicist and asked him to help me explain what's going on here. So we have to understand the limit of this time-ordered exponential when this initialization W naught goes to 0, and so the length of the time-ordered exponential becomes very large. And we want to argue that at the limit direction, then we can pretend it's commutative or something like that. Okay, okay. Let me give you. Okay, I'm out of time, but I'll still give you quickly another example, oops, you already said the answer before I answered the solution. Okay, so another example from implicit regularization that you get here is if you have a logistic regression problem. So you can think of it as what's logistic regression? These days I'd call it training a neural net with a single unit. Okay, that's logistic regression. And the problem is, again, underdetermined in the sense there are many, many different separating hyperplanes. Okay, so the problem, there are many ways to separate the data. And if I minimize the logistic regression objective of gradient descent, I'll definitely get to a separating hyperplane. But the question is which separating hyperplane? Okay, there are many separating hyperplane. And it turns out the separating hyperplane I'll get to is exactly the hard margin SVM solution, so the max margin solution. And this is, again, even though I did not in any way have neither margin or hinge loss or norm as part of the problem formulation. All I had is logistic regression. Okay? Okay, but now you can ask me, well, what happens if I have more than a single unit in my network? So if I have a fully connected network with linear activation, so we talk about linear networks, it turns out that all this doesn't matter. I'm still going to get to a hard margin SVM solution. Where things become more interesting is when I have a linear convolutional network, and then I'm going to go through this part really quickly because there's no question at the end. It turns out that what I get is sparsity in the frequency domain. Okay? And now also the depth does play a role. So fully connected network, the depth did not play a role. Here the depth does play a role. With a single hidden convolution layer, I get L1 norm in the frequency domain. If I have L convolutional layer, I get the kind of bridge penalty in the frequency domain, LP norm for P equals 2 over L. So with more depth, I get more sparsity in the frequency domain. Okay, so it looks something like this. But let me actually summarize here. So these are, oops, all my animations are gone. This is what happens when you lose laptops in the plane. So what I want to emphasize in all these things is all of these are examples where I'm optimizing over all functions. Okay, so you saw so far the top two. So this is all functions here are all matrices, right? I reparameterized my matrices, but I did not constrain them. Okay, and yet when just due to this reparameterization and searching over a particular parameterization, I biased myself to a very interesting and rich solutions, namely low nuclear norm solutions. Okay, and again, we don't completely understand this. Here, all functions was all linear functions because I just talked about linear neural nets. Neural nets are just an overparameterization of linear functions. By doing this ridiculous overparameterization and optimizing it, I actually, again, got very rich bias. I biased myself towards sparsity in the frequency domain. This did not come from explicitly injecting it into the system, nor from constraining it. I mean, I just optimized it over all functions, but using specific dynamics. And the third example, now we're actually going to talk about nonlinear networks, so it will be all functions. So let's talk about a model where you have one hidden layer with an infinite number of units with the ReLU activations. So now I can represent really any function, right? And I'm going to look for, going to start with networks with a single input unit. So I'm just going to talk about functions from R to R. I mean, that's still pretty rich. And using such an architecture, I can represent any function from R to R. But if I train a neural net, if I actually train this, it turns out that what I'm doing, I'm not going to get to just any function that fits the data. What I'm implicitly minimizing is essentially the second order total variation, the integral of the integral of the absolute value of the second derivative of the function. Okay? And so again, I'm actually doing something sensible here. I'm essentially reconstructing linear splines, but this is not coming from some explicit constraints that I put in there. It's just coming from my choice of a parameterization of all functions. Okay? And I want to also emphasize that both these and these, so this relates to some discussion before, maybe from Stefan's talk, these are not RKHSs. These are not kernels. So I cannot, this is it's a very sensible constraint over functions. It does not define an RKHS over function. So I cannot get this type of inductive bias by choosing some clever parameterization and then just doing a linear predictor over that. Okay? So this is in one dimension. And to get this, you actually, the key here is that the ReLU is the Green's function for the second derivative. Once I told you that, it should be pretty easy to actually derive this result. And what we're still trying to figure out is now this is with a single input unit, what happens with more input units? And again, this is something that, I mean, I'm not at all used to working with these transformed function spaces and Green's functions. I mean, this is all very foreign to me, and it's a place, again, that I think can use a lot of help. But so let me actually just jump to here, because I'm surprised I'm not cut off yet. So I think that if I look in general in these problems, I think there's a lot of space for help from especially statistical physics, and I think there's three particular properties of the type of work we're doing in understanding deep learning that's particularly amenable to tools from physics. One is that what we're looking at is systems with a large number of units. So as I said, the success of deep learning is really, I think, came from the fact that the networks are huge. They're way over parameterized networks. In fact, my view is there really are infinite networks. The only reason we're using a finite network is because the same reason that, so okay, does anybody here, do you use reals in your computation? Does anybody here use real numbers in their computations in computer? Or only integers? Use real numbers? Nobody use real numbers? What? What? Complex, great, complex numbers. Do you actually use complex numbers? No, you don't. Right? I mean, what you actually do is you use floating point representation of complex numbers. So why do you use floating point representations of a complex number and not an actual complex number? It's not because you think that by limiting to 64 bits, okay, complex number maybe use 128 bits, you actually get better statistical properties. It's because you think that 64 bits is close enough to infinity in order to represent a real number. Okay? The only reason you're limiting to 64 bits is that's what you can easily handle in your computer. For the same reason, I would argue that when we use a network with some number of units, the only reason we're using that network with that number of units, we're really trying to approximate an infinite size network. We're using that because that's what I can handle in my computer. I mean, if I had more computer, I'd use more units. Okay, and so really the object we should be studying the same way that when we're studying real and valued computation, mostly we're studying how things behave on the reals. And then there's also this issue of actually studying how the floating point representation actually captures them. I would argue that also here, really what we should be studying is how does learning with actual infinite number of units work like, and then we should also understand how we can actually approximate that with a finite number of units. And so really we're talking here about systems with a very large number of units, and it's even better than physics because it's not only number of units goes to infinity, really it is infinity. Okay? And this is, I think, a situation that really is nicely captured by many tools in statistical physics. I think this is the problem when dealing with in many units. Each one of them follows a very simple rule, a very simple law that we can exactly state that law. And what we're interested is in not understanding any particular unit, but this macroscopic behavior of what is the function that's being represented here. Okay? The other thing is the dynamics are also very important. It's not, as I hopefully tried to convince you, it's not just understanding what the ground state, what are the zero error solutions. We really need to understand the dynamics of the training. And again, this is something that I think we can borrow a lot of tools from physics. And the third thing is a type of study is a bit different than the type of study that maybe in traditional machine learning, in that we're not, we're trying to understand an actual observed phenomena here. So deep learning works. This is like, it's a phenomena. And now we're trying to understand it, rather than we're trying to build a system that does something. And so the type of also methods we're using are some combination of observational studies and what is it that works, experiments, simulations, and building models. This is exactly the type of process in physics, and is fairly different than in machine learning, and I don't think we're very actually accustomed to doing that. I also want to point something relates actually to Lenga's talk. I want to contrast this view with, I think, a more so the 1990s. In the 90s, there were lots of work in statistical physics for machine learning, and most of it, the way it viewed having many particles, was it viewed as every data point as a particle. Okay? This is similar, I think, with what Lenka said, where every node is a particle. But the problem is, in this case, in order to make the statistical physics work, you have to assume some law, and usually a fairly simple law, on these particles, on these training examples. And this I kind of don't feel very comfortable. I mean, it's nice to do this analysis, but I never felt very comfortable in this style of statistical physics analysis machine learning, because these examples, these are very complex objects. We don't know what law they follow. These are like images or something like that. We don't know what law they follow, and it's definitely not a simple law. Okay? And I think that now, if you go here, that this is much more, I think the statistical mechanics view of this is much more representative, because these are, if I look at the particles as the units are really, we know exactly how they behave, what's their law, and that they are indeed very simple. Okay, my guess is I should stop probably, right? Because
Probably, but you have something poignant to say.
no, I mean, so what I wanted to, I think I should, what? I think I should stop. Oh, something. What? Maybe I'll just.
Just tell us. I mean,
Okay, sure. I'll just tell you. Let me just jump to here. Okay. So this is just like, yeah, exactly. So okay, so when I this is a slide from my first lecture on machine learning, and I try to frame machine learning. And so the question is, what is machine learning? And to me, machine learning is an engineering paradigm of being lazy, an engineering paradigm of performing a task instead of programming it by using data in order to to solve that task. And so the emphasis is really just in solving the task. And so what I get evaluated is just, do I do the task well or not? So if my task is face detection, right, then this is indeed Jim Simons, or I hope that United is now like has some system that identifies my laptop or something like that. Okay, and the problem is that I want to, what I want to, the reason I'm putting here is that the point I make, and I want to make it here also, is that I distinguish between machine learning and other discipline, other type of things that I have found somewhat arbitrary names for here that you can also do with data. One of them is knowledge discovery or data mining. And this is when you don't want to perform a task, but actually you want to understand. Okay? So you want to take your data and learn all kinds of rules about your data, okay, that explain your data. And what you're trying to is get some understanding. Okay? This is much harder than machine learning, okay? Because I think the success of machine learning is that we're dumping understanding out the door. We don't want to get understanding, and that's what allows us to actually use these huge overparameterized networks that actually are very good at performing the task. Another thing which I called here statistics, and I don't want to argue about what statistics actually means, it means many different things to different people, is much of the difficult part of statistics. And if you take a statistics 101 course, the hard part is not getting the estimate. The hard part is actually getting a confidence measure for it. Okay? And that's, and again, machine learning, we don't do that. And so it's much, much, much easier. Okay? And the fact that we don't do that, we're solving a problem that's actually much easier, allows us to be much more powerful. Okay? And I want to put a quote by Vapnik, that when you want to solve a problem, if a problem is performing a task, then solving a more complicated problem in the way, like getting some very concise and nice rules for it, just makes, we shouldn't do that, because it just makes the problem harder. We want to make the problem easier. We don't want to solve a harder problem in the way. Okay? And the reason I want to put here is when talking about physics, I think there's probably going to be discussion today in the next few days about trying to use machine learning in order to gain physical understanding. And I want to just point out that in my view, these things are very contrasting to each other. Trying to get an understanding is kind of the opposite of machine learning. Okay? The success of machine learning, I would argue, is exactly because we're using these super generic models that can capture anything without understanding. Okay, so now I really should end. Okay.
I mean, given that Nati has thrown so many provocative things on us, I believe we should have a few minutes of questions and discussions. Yes. It has to pop out. Is it popping out?
It was. Yeah. So thank you. It's a very interesting topic. And my question is, how does your conclusion is affected by the signal to noise level of the data? Because if the signal to noise level is really low, which means basically any global minimum that give you zero training loss will be a bad algorithm for the optimum.
Nice.
So yeah.
Okay. So that's an excellent question. Another important question we don't understand now. So what you're saying is that what we've been taught and what I teach my students is that what you generally should do in learning is balance your training error with your complexity. Choose some complexity measure and then balance them, right? So you don't want to overfit. You don't you want to find the kind of the sweet spot in between. It turns out that definitely in deep learning, and we actually can see this also in some simpler systems, you actually can learn also by driving the training error to zero. You don't learn any better than that. Is there a whiteboard here? Or? Okay, so if you just think of what happens when you change this trade-off. So I think of learning as a bicriterial optimization problem of balancing between complexity and error. And as I get higher and higher complexity and smaller training error, I expect it to go down and then up. And it turns out that it goes down and then it stays level for many problems. So we actually can get and this is, I think, Misha Belkin coined the term, this is the first one that really pointed out this is something our classic theory of statistical learning does not explain, coined the term interpolation learning. Then if you're in this interpolation regime, you just look at the minimum complexity, minimum norm solution that actually fits the data, you actually can generalize as well as if you do the optimal balance. And you can see this. So Misha has lots of work, for example, for kernels, explaining in some kernels that's not the case, but in other kernels that is the case. So there's some kernels that I would call interpolation kernels, in which you can get the min-max rate that you can get with an optimal balance, you can also get by finding the minimum norm solution. So this is so again, this is something we don't actually understand, and we're also trying to understand.
Yeah, I just want to point out the fact that if you have a very low signal to noise level, then basically you won't be able to observe that, even for like a linear model. And if you have like very large noise variance, then clearly, if you overfit the data, then the generalization error will be really, really bad.
So unfortunately, so it seems that that's so. I would disagree with this clearly, because it seems, at least empirically, and also we have some theoretical understanding, that in many models that's not the case. Now remember, we're talking about, so the thing is, in a linear model, you might not even be able to get to that zero error solution. There might not be a zero error solution. But in many models which are rich enough that there is always zero solution, and rather learning is by, so again, so you have to, the learning here is by, the learning rule you should think of is, minimize the complexity subject to zero error solution. That learning rule seems to be effective for many complexity measures, including for many linear learning problems for many kernels. So this is, I would disagree on the clearly part of your statement.
Yeah. So I find your definition of machine learning a little bit too restrictive. So it's true that there's this slogan and that is responsible for certain big successes of machine learning, because when you're trying to solve a problem, especially a difficult problem, it just, at a certain extent, it helps if you make it very specific and narrow it and say, this is exactly what I want to do and I don't want to do more, and so on and so on. So this was great like 15 years ago. But if this was all that machine learning was about, then I don't know, I wouldn't be so interested in it after a while. But my claim would be that these things are really intimately related, and the sort of things that we're learning from neural networks now, for example, are going to have an effect on the statistical side and on the data mining side, and actually are going to lead to learning something about the real world eventually. So these are not orthogonal directions, they ought to be connected directions. Similar to that, and let me just make the other comment, is that this division between the capacity of your model and the optimization. So I totally agree that the models that people are using today have huge capacity. So in the more classical division of labor in machine learning between the people who define the model and the people who create the optimization algorithm and the people who actually prove the bounds, it seems like they're almost like all equivalent, right? These convolutional neural networks are good enough that you could learn about faces or about chemistry or anything you want. But even if the function class is the same, the structure of the model, the architecture of the model also has an effect on the optimization. So I think what's interesting is not just the architecture by itself or the optimization by itself, but it's the interaction between the two. And that's what's actually difficult to get a handle on, and very little work has been done on it.
Okay, so let me answer. So there are 2 points here. One is how can success in machine learning inform us about the other disciplines? I think we have a slightly more different perspective and opinion about this, but it's difficult to argue about. I mean, it definitely is possible that the success in machine learning would inform it, but I guess the point I was making was I think that in my view, the root of the success is exactly is almost antipodal to the type of thing you really want for understanding. But maybe this is a longer discussion, maybe for lunch. In terms of the interaction, so yes. So I mean, I glossed over things a bit, but there's definitely I'm not saying that the choice of architecture is irrelevant. The way I think the choice of architecture is very important is the choice of architecture determines the parameterization. So so you can think about it as really I'm interested in all functions, right? So I'm optimizing function space, but I'm choosing a particular parameterization of them. And in the parameterization space, I'm probably doing something fairly simple, still guided by optimization algorithm. So my choice of optimization algorithm guides what is the geometry in the function space. But the choice of architecture determines this link between the parameter space, the choice of optimization algorithm guides the geometry in parameter space. But the choice of architecture really is the choice of parameterization, creates this link and this is really what creates the really rich structures. So I completely agree with that point, but still I think the optimization dynamics are key inside there. And it turns out that you can't completely separate them. So we tried to study these completely, to completely decouple them, and it seemed to not actually work. in some technical sense.
Thanks, Nati. You should consider losing your laptop more often. It was a great talk. But so I have a question. So there is, it's a well-known fact that you can actually do compression on neural nets and not lose anything on your test data.
Right.
So you can compress this huge network to a much, much smaller
Right.
one. So there seemed to be a way to rotate in this space of functions that generalize well between a very sparse sort of represented model and a very maybe rich where you have sort of all your parameters in, but so they're constrained somewhere. So can you maybe comment on your vision on that?
Yeah, I mean, I'm not okay. So yeah, that's true, and I think that what might be here is that once you you have to. My vision of this is very much influenced by the dynamics. So you have in order for the dynamics to guide you to the right place, your network might have to be very, very large, right? If you restrict your network initially, you're really not, the dynamics you get are not the good ones. Once you're already there, then note when you're compressing, you're using a very different type of mechanism kind of to compress it usually. And there you might already have strong enough signal to allow yourself to not you don't care anymore about those dynamics in some sense, right? I mean, I don't know if this explains it, but this is definitely so when you initially actually the experiments I showed at the beginning came exactly from trying to understand what happens when you add units or remove units. So we thought that initially we thought that it's all about optimization. That having larger networks just allows you to solve the optimization problem more easily. Which I don't. That's not. That's true, but that's not. I don't think that's the whole story now. And so this compression view, I think, comes from that perspective. Let's use a large network to make the optimization easy, to bypass the local minima, and then compress it down. And I think that the story is a bit more complex than that. That making it big also influences dynamics and helps you. But I don't have something too intelligent to say about that.
Elaborate on the remark of Rizi.
Right.
We see clearly these 2 points of view. On one hand, there is this approximation point of view, and then the optimization.
Right.
If you take, for example, I came just before, I begin essentially by saying, let's forget about optimization.
Right.
Let's concentrate on approximation. And at the end of the talk, I arrive to a problem which is in fact an optimization problem, because dictionary learning is an optimization problem. Now, if we follow your talk, you begin by saying, well, there is really no approximation problem. Approximation problem is solved in the sense of O of t. I caricature, I'm sorry.
Okay, yeah, that's fine. Yeah.
And really there is an optimization problem. However, in approximation theory, what you do is not trying to optimize with a certain number of arbitrary parameters. You try to optimize so that there is an easy algorithm which finds the optimal. That's what you do when you have approximation space, and then you say there is a good approximation. It's an approximation which is found with a simple algorithm. If we follow your whole talk, what is interesting is that in fact at the end, you arrive to an approximation problem. Because when you say my optimization algorithms is finding a minimum nuclear norm,
it is an approximation.
You arrive to an approximation problem because there is no reason that this minimum nuclear norm will give you a good approximation. In other words,
I completely agree. Right.
In fact, come back to approximation.
I completely agree.
And I think, to come back to what Rizi was saying, the problem is at the interface.
Okay, so I completely agree. Sorry.
Yeah.
Okay, so I completely agree. And in fact, it's not that I don't think that there's a question of approximation. In fact, I think the question of approximation is much more interesting. Because I started with the saying that the question of approximating in unrestricted neural nets where you're just restricting by the architecture, is kind of boring in the sense that, in the two senses I said. I mean, if you're allowing very large networks, you can approximate everything. And if I'm constraining the size, I can still kind of approximate. It just becomes a question about circuit complexity. Not that I'm suggesting circuit complexity is boring, but I mean, it's kind of, we kind of know the high level answer, okay? But what we're seeing that the real approximation problem we're solving is an approximation problem with a complexity measure that we don't know what it is. So I would argue that when I say I want to understand deep learning, to me now, in addition to this magic property, the main thing, maybe I should have made it red, is trying to understand that first point there, is that what we're really searching over the space of full functions, but we're searching over the space of full functions trying to find something which has small complexity. Like, for example, in the metrics case, it's the nuclear norm. Okay? What I want to cover is that nuclear norm. What is the complexity that I'm actually trying to minimize here? And when I understand that, and now I can ask both how is it that my, link that with optimization algorithm, in the sense that how is the optimization algorithm actually doing that, also implicitly and under what assumptions, and ask the approximation theory question, which is, or the question about reality. I mean, this is the two coins, two sides of the coin of what is it that I can represent well with low complexity, low nuclear norm, like low what. So I still think that there's so let's take the metrics factorization as an analogy, right? Once we understand. So okay, I could have started by saying I'm going to fit a low rank model. Right? Suppose I know, if the data is approximately low rank, I started with approximately low rank model, and then the question of approximation is very clear. I can tell you, if I have something that's approximately low rank, I can approximate with a low rank model. And the whole question is a question of computation of can I actually fit this low rank model? Okay? Now, instead, I'm fitting this way over parameterized model, and my complexity is not explicit in my formulation, because my problem formulation was just I'm just going to do gradient descent on this way over parameterized model. And the result of the study is that we identified the complexity measure, which is the nuclear norm in that case. So now I actually know what I'm doing there. And now you can ask both the approximation question of, what can I actually represent well with low nuclear norm, and the question of how does that help me to generalize. Does that go towards?
Yeah,
I think that
my impression is that then you are a bit self-contradicting relatively to the last slide. Because in approximation theory, what we know is that then complexity is directly related in a dual form to some form of regularity and model. So you cannot speak about complexity and this problem without speaking in some sense about what is the underlying model. In other words,
the model of the data or the model?
No, the model of the functions.
The model of the function, okay, because I separate between these two.
Model of the function,
yes.
And therefore these different boxes you were showing, which is understanding the structure, understanding the statistics, and doing machine learning, they are like that. Because if you say it's an it boils down at the end to an approximation problem, then it can only work because you are in a small functional space, and therefore there is some form of model or
so the thing is that when you say small functional space, that functional space can still be huge. Because okay, so the question is okay. Let me try. So the thing is, I'd argue that the space you need in order to get understanding is much smaller than the space you need in order to successfully learn, especially when you have a lot of data. Okay, so it's not a surprise that the success of machine learning came when suddenly you have tons and tons of data, because the size of the model, if you want to get good performance in a task, the size of the model class you can handle increases with the amount of data you have.
But you don't have much data in high dimension compared to curse of dimensionality.
No, but I have because we still have, even in high dimensions, we're still looking at some restricted model in high dimensions. So I agree with you that of course you have to restrict the model. But what I'm arguing now is that the restriction in the model to get good performance in terms of machine learning can be much, much, much bigger than the type of restriction you need in order to get good understanding. Because once you have more and more data, you can allow yourselves, the size of the model can increase with the amount of data. But to get understanding, it doesn't increase. I mean, what I can understand is still, it doesn't matter, help me that I have more data. What I can understand is still fairly limited. It's still something you can write down, I don't know, in 3 equations or something like that, okay? I mean, beyond that, I can't really understand. And so once you have more and more data, these two things start diverging from each other significantly. Okay? So in particular, if you get for a second computational considerations out of the question, we do have a universal learner. So if you just either use neural nets or even do something like so another way to view it is that machine learning without computational considerations is very boring. Right? I can give you an ultimate learning rule. Just find the shortest program that fits the data, or that balances fit for the data and errors. That shortest Python program that fits the data. That's an amazing learning rule. I'm willing to bet you like multiple 3-star Michelin dinners that this learning rule beats any of Jan's networks. Okay, it beats anything. This is really the ultimate learning rule. I mean, we can't implement this because we can't do it. It's not computable. But if we set aside the computational, we do actually have universal learning. And so learning in some sense is very easy. You do not have the same type of solution for the understanding problem. If you did this, the type of problem, the program you would get would not be something understandable. It would be like gobbledygook. Okay, so okay.
I discern, by the way, a certain nervousness on people's faces with respect to lunch. So we will
Sorry.
the short talks. Well, everything is in flux. Lunch is holy, so we'll
Okay.
have lunch after this. But let's have two more questions.
Okay.
I have a question about the magic property. So when you introduced it, you motivated it by the NP-completeness of very simple learning problems. So that was worst case hardness, but the
Right.
worst case was with respect to the data.
That's true.
Right?
The
So one would expect that this magic property will relate to the data and its
Exactly.
distribution
Yes,
model.
it's exactly your third leg.
But then during the rest of the talk, you never came back to the data. You were talking about the optimization.
Excellent. Okay, excellent question. Good. So, right. So the magic property definitely relates to the data. This is a magic property of the data. It's exactly the. I really liked in your talk the three legs there. It's exactly that third leg. So only two comments about this. One is that the magic property, you can think of the magic property that I had. So first of all, I didn't answer this, which is maybe why I didn't get to the data, because I still don't know what the magic property. But one part of the magic property, if you ask me, what functions can I learn? So for the matrix factorization problem, for example, I know what the magic. I kind of know what the magic property. The magic property is having a low nuclear norm. Okay. So there, that's relatively easy, and then I have a nuclear norm, and I know that if I have low rank plus incoherence, that gives me low nuclear norm. So you can think of the magic property as having low rank plus incoherence, for example. Okay, so there I can exactly tell you what the magic property, and this is definitely a function of the data, right? A property of the data. For neural nets, I don't know what this magic property is. And when I talk about the properties of the data, there are two parts here. The properties of, let's call it X, and of Y condition on X, right? Of the labeling and on X. I focus on this talk a lot on Y condition on X. So when I talked about these things, all of these really are talking about Y condition on X, and what is the function computing. And so this says the magical property is that my function has bounded second order bounded derivatives or something like that. Okay, second order total variation. Sorry. Okay, but that by itself is not the complete answer, because you also need the optimization to work. Okay?
Because the NP completeness, that was for a given Y
given X, right? So I think the magic property is both of Y given X and of X, and I mean I definitely don't have the answer. I think a difference in approach maybe versus the approach you presented is what I prefer, and this also maybe in the matrix factorization case comes up most clearly. I prefer not, so in your study, you start by instantiating all three legs. So you start with a particular model on the data. You say, the data is, follows this particular simple model. And then you understand for those three legs, how it behaves. What I would rather see, which is much, much, much harder, and because of that maybe we're not succeeding, is I want to instantiate two legs. So instantiate the other two legs and try to work backward and say, what is the property I need that with the minimal property that I need that will allow it to work? Okay, because I don't. I feel that looking at these super simple models sometimes leads us a bit in the wrong way, in the sense that things work because of the very. So in particular, these are all very symmetric, homogeneous, kind of like spherical, and sometimes they make things work because of reasons that are kind of orthogonal to right. So.
Defend that point of view is to establish a kind of zone
I agree.
for which it will work,
for
which it will not work, and then to do this in between this.
Yeah, I agree, and I'm also interested in that type of work, and I read these papers very eagerly, but somehow I'm just trying to emphasize here the kind of difference between, but definitely the magic property is exactly what is the assumption in that third leg.
Let's have Finn. I'm sorry.
Yeah. Sure.
Yeah, I'll be quick.
Sure.
So
Okay.
yeah, I just want to push back on your like static description of these different fields of data mining,
Yeah, I mean, that's,
statistics, and
there's-
machine learning, right?
Sure,
The
that's very
fields are
easy to.
evolving, and
Yeah.
I would see machine learning as part of statistics, and I really push back on characterizing statistics as only p-values.
All right, I know.
and all
Hey,
that,
I
right?
had
mean,
confidence intervals.
Come
there
on, we're
also.
very modern, we evolve, and
No,
I want to own machine learning. So
I agree.
that.
I agree, and I mean no offense here. This is a caricature where mostly what I'm trying to emphasize here is that machine learning is much easier than many problems encountered in statistics. I'm not.
But I
trying
also
to,
think when you have more data, your understanding also get deepened, right? So it's not like understanding doesn't change. If you look at genomics, people have all kinds of data. It's not just RID, you have N go to infinity.
Right. So I agree.
Understanding also gets better.
I completely agree. So when you have more data, your understanding can get better. But what I would argue is that I'm feeling I should say more comfortable talking about this and that. I mean, what is statistics is like, I mean, I've spent way too much time talking to like Mike about like what is statistics, and I don't want to get into that. But the thing is that when you have more data, your understanding definitely gets better. But the way in some sense, I think it should get better is that when you have more data, it allows you to have, in some sense, a smaller, tighter understanding. Like you want to ultimately. I judge how good understanding you have by how small this description. You really want to have something tight and small. And having more data, I think, allows you to do that. But I would argue that in a very different way than it allows you to do better, to perform the task better. So you can.
Again, you have a fixed target, I agree. But if you look at science, the target is moving too.
Sure.
Right? So in that sense, you also get better understanding.
You're right. So you can get understanding for more complex situations, for sure. Yes, I completely agree.
Yeah, I'd just like to pick up on one thing you said, which my experience disagrees with, and that is about the declining influence of bringing in expert knowledge. So I can think of lots of examples that I've experienced recently where the only way you make progress is by using some huge data set that's nothing to do with your problem to sort out things using expert knowledge from those big data sets. So then you have to use those tools you developed on the small real data set you're actually really interested in. I mean, a concrete example would be I use face and emotion in faces to understand people's evolution of psychiatric illness. There is no way that I can enlarge that data set so that I could learn the facial expressions at the same time as actually understanding the progression of their illness. So you have to get your expert knowledge in one place with one data set, and you use it on another one. And I think your model is convolving those, and I think it's a mistake, actually. I don't think it's the way it's going to work at all if you want to do things with small data sets.
That's probably true. So again, that's probably true. And again, I think that this is of course a caricature view. I think that as I view the goal of machine learning and developing in tools in machine learning is to allow you to rely less and less on expert knowledge, and especially both on expert knowledge and on having to program that expert knowledge in. So in order to do that, you have to trade off that expert knowledge with more data. Okay? And so there are two things or several things you said that I think are very important points. One is, of course, if you have a small amount of data, then you're really limited in your ability to do that. And again, I think that from my perspective, really, this is a very subjective view of the kind of the ultimate goal of machine learning is to be able to push things more and more to this end, so that you can rely on minimal amounts of expert knowledge, maybe some very crude invariances, very, very crude expert knowledge, and just rely on loads and loads of data instead. Now, when you have limited data, you're much more restricted in how you can do that, and you definitely need to bring in expert knowledge, and you definitely gain for more expert knowledge you bring in. I don't think I said that you necessarily hurts you when you bring in expert knowledge, although maybe we talked about it yesterday. In some cases, it does. But the other thing is that I don't remember it now. There's another point you made that I agreed with, but I don't remember. Yeah, so yeah, we can say that. But definitely I agree with this, and I think this is great. I do think, though, the point I was trying to make here really is what I've used the kind of if I do a projection, a PCA to one direction, what is kind of the primary, the principal direction of machine learning? And I would argue it here. This is the principal direction, like moving from expert knowledge, not relying on minimal amounts of expert knowledge and more and more data.
Okay, let's thank Nati, and we will have less of Nati.
Sure. Thank you.